There's another formula in section 9.3 that involves an integral, but it's not to compute arc length. It's to compute a surface area. A surface area of a solid of rotation. For sake of simplicity, suppose you got a parametric curve that is moving up and to the right. So again, I can think of this as a point function, xy equals f of t, comma g of t. As t varies over some interval from a to b, say. Notice this is an xy plane. So it's not necessarily the case that this is x equals a and this is x equals b. A and b are limits on t, not x and y. Actually, the textbook uses different letters. They use T1 and T2, maybe to really emphasize that to you. T1 and T2 in the textbook. Again, for emphasis, this number on the x-axis is not necessarily A, and this number here is not necessarily B. They're probably not necessarily T1 and T2. You're parametrizing the curve over some interval that you picked. The T1 and the T2 might have nothing to do with these values here. We'd like to figure out the surface area obtained by rotating this curve around the x-axis or the y-axis, for that matter. And it'll be a different surface area. This is kind of analogous to what you might remember from Calc 2, where you take curves and rotate them around an axis and you find a volume. But in that case, you're finding a volume where you've represented the curve as a function, y equals f of x, not a parametric curve, but a regular graph of a regular function. So one difference is we got parametric equations here, and a parametric curve, not a regular curve. Another difference is we're finding a surface area, not a volume. You rotate this around the x-axis, you'll get a solid. We try to do a mirror reflection of this curve up here. Kind of a sideways bell-shaped. You're trying to imagine the ends are open. Open end here and an open end over here. So you're not trying to find the surface area of the ends. You're trying to find the surface area of the part around the sides. Goal, find the surface area around the sides. What do? Well, I could just write down the formula, but it's really ultimately more beneficial for you if we try to imagine deriving it. So I'm about to try to derive it as a scientist would. This is not easy. And it's easy to feel like you're going to get the wrong answer when you're doing it. But it's something worthwhile to look at. Keep practicing. What'd you do in Calc 2 when you thought about volumes? You thought about slicing the solid with thin slices of a certain width that you might have called delta x. We could do something similar here. We can slice the solid with a bunch of thin slices. And yes, you could call the width delta x, but we're not. We're going to relate this to arc length along the curve. And that turns out to give the right answer, whereas if you think about it in terms of delta x, it gives the wrong answer. Imagine zooming in. Well, let's zoom in up here. Imagine zooming in up there to a little piece of the curve that is a little piece that you're rotating. What could I call the arc length of this? Delta something? I could. This is a little weird, but the standard letter used for arc length is S. S does not represent speed. Or represents arc length. I'm sorry, that's the way it is. So I could call this delta S. I'm going to do something a little weirder, but somewhat consistent with sometimes what you see in your science classes. I'm going to actually call it ds. ds is imagined to be an infinitesimal amount of arc length. It's infinitesimally small. What's an infinitesimal? It's a positive number, smaller than any positive number you can imagine. So is it smaller than 10 to the negative 10? Yeah. Smaller than 10 to the negative 100? Yeah. Smaller than 10 to the negative a billion? Yeah. Much smaller. 10 to the negative Google? 10 to the negative Googleplex? How far do I have to go? It's smaller than all of those. It's smaller than any positive real number, in fact. That's how small this is in your imagination. That is, technically speaking, nonsense in the standard real number system. There is no such positive real number that's smaller than any positive real number. Doesn't exist. You can always take a positive real number and divide by 2 and get a smaller one. But we pretend it exists for the sake of getting the right answer and developing intuition that's still helpful, even though such a thing doesn't exist. When I was in your shoes and sitting in those science classes and my teachers would talk this way, I'd be like, how do you know you can do that? And the science teachers at least would just say, what are you, a mathematician? Like, yeah, I'm a math major. And they'd say, well, okay, ask the mathematicians how. To us, it just makes sense. That's how we always think about things. They don't try to prove it. Can it be made rigorous? Yes, though it's really, really, really hard. It's called non-standard analysis, and it's a really hard. I grabbed a book on non-standard analysis out of the library, looked at the first page, and I put it back. It was too much for me, even, okay, to do it rigorously. So it was good enough to just think intuitively. If that's ds, and I draw a right triangle like this, based on the coordinate system, it kind of makes sense to call this dx and this dy. And on this infinitesimally small triangle, I could use the Pythagorean theorem and say ds is square root of dx squared plus dy squared. Oh, and this can even be related to speed. Guess what? This is a side comment for the purpose of, well, I guess it's not a complete side comment for the purpose of figuring out the surface area, but we can relate this to speed. Actually, this is important. What I can do is a little trickery. Write dx squared as dx dt squared times dt squared. And dy squared is dy dt squared times dt squared. You've never done this kind of thing before, maybe. I'm doing something else that's kind of a no-no. I'm treating these dx dt's and dy dt's as if they're fractions. Right? But that's a common thing to do in science, is pretend those are fractions, even though your math teacher always says they're not. It gets us the right answer. It's not good enough. We're after the right answer. And the dt squared can be factored out. And you could square root that separately. And what's the square root of dt squared? I guess it should be dt. Or maybe absolute value of dt. What? I don't really want to feel like putting absolute values in there. Okay, let's just pretend dt is a positive infinitesimal number, so I don't need absolute value sets. Guess what? This is the speed. The formula for the surface area is going to involve the speed along the curve, amazingly. Not only the speed, though. What else is it going to involve? what should I call that? The surface area of this thin slice. Maybe I should call it dA, A meaning area. dA, the surface area of that thin slice, should be its circumference times ds. Circumference ds. Circumference of a circle times ds, the length of the side of the thin slice. Should that be its surface area? I hope that makes some sense. I mean, you could try to make more sense out of it by imagining taking a scissors and cutting this and unrolling it into a really thin rectangle. The base of this long thin rectangle is going to be the circumference of the circle, and its width is going to be ds effectively. But what's the circumference? The circumference is 2 pi times the radius, which I'll just write as radius. Yes, the C is circumference. But what's the radius? In terms of the parameterization, it's the y coordinate. It's this distance right there, which is g of t. G of t is that distance. That's the radius of the circle that I'm kind of trying to draw with three-dimensional perspective. This is 2 pi g of t ds, and then replace ds with this thing. dA is 2 pi g of t times square root of, now go back to f and g inside, f prime of t squared plus g prime of t squared dt. And then the total surface is found by integration. So total surface area. Surface area A is found by adding up the dAs, integrating them, which means ultimately integrate this thing. 2 pi g of t square root of f prime of t squared plus g prime of t squared. If you use my notation for the limits of integration, A and B, you'd go from A to B. The textbook would use T1 and T2. There's your formula, your amazing formula for the surface area around the sides of this solid of rotation, found by taking a parametric curve and rotating it around the x-axis. Technically speaking, to use this correctly, the author really emphasizes this, it's assumed that g of t is not negative. If your g of t function is non-negative, if you go below the axis before you rotate, you'd want to flip it. You'd want to consider the corresponding curve with negative g of t, which would be a positive quantity instead of a negative one. What if we wanted to rotate it around the y-axis instead? It's the exact same curve, but now you're rotating around the y-axis. It'd be a very similar derivation. What changes? The only thing that changes in the end is having an f of t there instead of a g of t.